Okay, so does anybody know what the three main components of deep learning are already? Good. I'm always afraid that there are people who cannot hear this question anymore. In my courses, I like to ask these questions every time, in every lecture that I give, because believe it or not, machine learning and deep learning, everything revolves around different design choices for three components. And now I will try to explain to you these three components step by step. So the first component is data. Yesterday I read a paper titled Data-Free Machine Learning, and I was thinking, okay, this crashes my point of view on machine learning because this is the main component. So you need data to do machine learning. I didn't read in detail the paper, but yeah, maybe I should. I'm really interested in data-free machine learning or data-free learning. We need data. So without data, there's no machine or deep learning. Then the second component is a model. And what sets deep learning apart from machine learning is in deep learning we use a specific type of model. The model is obtained by a graphical structure, a signal flow chart that explains how the input features, I will tell about features in a second, are translated into a prediction, an output. And this signal flow chart is called artificial neural network. And all deep learning uses artificial neural networks, in particular deep artificial neural networks. I will explain what deep artificial neural networks are in a second. And still we need one more component that tells us how good is a model. If you don't know how good a model is, you cannot learn. This is also related to the fact you can only learn from mistakes. So unless you do mistakes, you will not learn. And to find out the mistake, you need a loss function. So also this I will discuss in some detail. Yeah, and again, please interrupt me at any time by raising a hand, for example, or raising your voice. Okay, so in a nutshell, what machine learning and deep learning is about, it's about fitting models to data to make accurate predictions or forecasts. There's no magic going on, it's just fitting models to data, and it turns out that a specific type of model based on these artificial neural networks can be fit to very large data sets. Yeah, and this also is done in our brain. So when you look at this sequence of numbers, what is your guess for the next element? 9, why? It's a sequence, yeah. So what you did in your brain, or what I would do is, I look at the data, so these numbers are data, this is data that I observe, and I try to fit a model. I try to make sense of the data. And one type of model is just a linear, straight linear line. So so this is just a model, because there are infinitely many different straight lines, so I try to fit the model. So I pick one straight line that fits best the data, and it seems the best straight line is increasing by 1 from one element to the next element. That allows me then, so then I have fit the model to data, and after I have fit or learned or trained the model, I can make a prediction. I can look outside the training set. This is then called forecasting or predicting. Okay, yeah, and this is already including two components. Data, so these numbers here is the data points. Then we have a model, the set of all possible straight lines, and one such straight line is what I call a hypothesis. So a hypothesis is one possible function that translates the position of the sequence element to the number on that position. So you try to find a good hypothesis for this data. And this is what deep learning algorithms do. Okay, any questions at this point? So this is the deep learning principle. Fit models to data in order to make accurate predictions or forecasts. Yeah, so I highlighted here model and data. Where is the third component coming into play here? Loss function. What do you think? Where do we need a loss function? Here, yes? Accurate, exactly. How do we know if something is accurate without a loss function? Without a loss function, we cannot tell if the predictions are accurate or not. For this, we need a loss function. Okay, so let's start with data. And I want to emphasize that I agree with this famous scientist, Andrew Ng. What's the correct pronunciation? Andrew, I think he's from Stanford, and he claims, or supposedly claimed, that it's more important to improve the data than to improve the code or algorithms, and I agree. So the challenge is to model the data well, to compile the data well, to choose the right data. This is the more challenging part. Using deep learning models is 1 or 2 lines of Python code, typically. Okay, so what is data? In the most general sense, I like to think of data as a set of data points. And this is more general than, for example, bits. Bits or bytes or files on a hard drive is just one very small, tiny part of data, of possible data forms. So what is a data point? Data point is any object that can carry information. Can be a number, can be a protein, some protein. Another example of a data point, a partial differential equation. Why not? It's an object. Another example, a bridge. We would like to know something about bridges. Or a cow. Data point could be a cow, an object that carries information. This is an analog data point, so I would not consider it digital. It's not bits, not bytes. It's a cow. Yes, so an object is characterized by its properties, and I like to, or I think the machine learning literature largely distinguishes between 2 types of properties. So they are called either features or labels. And features are the low-level properties that you can measure easily or compute easily. So whenever I give you a feature, which is a number, like 10, then you could say, well, I can take 10 to the power of 2 is another feature, because you can compute it easily if you can compute powers easily. The other type of property is what I call a label. So this is the gold, so to say. This is the gold in the data. This is what we're interested in. This is high-level information, quantities of interest, which are difficult to determine or measure, and for which we want to use machine learning or deep learning to predict the labels. So in this course, features are mostly numbers. So when I talk about features, I mostly mean numeric arrays. Maybe the most widely used example for features of a data point are the color intensities of an image. So you take an image, which might be a pixel bitmap, 512 by 512 pixels, and each pixel is characterized by the red intensity, green intensity, and blue intensity. So these are all numbers that you can stack into a vector, rather long vector. It's 512 to the power of 2 times 3. So it's already quite a large vector. But this is a natural way to construct features for an image. Okay, and then you might say, okay, but what if I don't have an image? What if my data point is something else, like an audio recording? Well, you might have learned methods to visualize audio recordings, like draw the graph on a 2-dimensional plane. So this graph of an audio recording is like an image. Or there are more fancy versions, which I worked during my PhD studies, which are time frequency energy distributions. So at which time, which frequencies are mostly active in the recording. And again, you get an image. So as soon as you can make an image of your data point, you can use these features. Does anyone know a scientific field that studies methods to make images of different types of data? How is this called, this field? What do you want to do? You want to visualize the data. So visualization, data visualization, revolves around ways to make images, pictures of different types of data. Also, I've shown you this example before. Here, I represent a data point, which is a protein, by a picture. In reality, this is way, way more complicated data point than just this picture. But still, I have now a picture, and I could now take the red, green, blue values of these pixels to characterize a protein. Or the cow. I just make a picture of the cow and get the red, green, blue values of the pixels as the features. Or this might also work for human faces. So you just take a picture of a human face and know, okay, this guy has a bad liver. So this is already quite generic. Basically, any data point, for any data point, you get features like this. What could be a quantity of interest? For example, for a cow, what could be the high-level information for a cow. How much milk will it give? And the features could be the statistics or the status of the pregnancy. As I understood, you can only get milk from a cow if it's pregnant or has been pregnant. So we can predict the amount of milk harvested from a cow. Another example for the data point, what could be the features? Well, if you look at the physical system that is modeled by a partial differential equation, for example, as I understood, the brain signals, human brain signals are sometimes modeled using partial differential equations. What you see is not the partial differential equation itself, but you see the physics, the signals that you measure. So you see the solutions. You see a solution of the partial differential equation, and you want to work backwards. What is the corresponding partial differential equation? Yeah, so that was a quick recap of features and labels of data points. And just want to point out here that everything that I talked about are design choices. So it's you who decides, when you work as a deep learning engineer, you decide what a data point is. You choose the data point. You choose the features and the labels. For example, if you look at some raw data from the Finnish Meteorological Institute, there are many different ways to compile, to frame this raw data into data points. You could say a certain period of time is a data point, and you're interested in predicting as the label the temperature on the next day. Or another choice would be, the label would be the temperature of 5 days ahead, or the temperature 20 days ahead. So you get different machine learning problems by choosing different labels. And these different choices of label might result in machine learning problems with varying difficulty. It might be easier to predict the label being the temperature on the next day than being the temperature 20 days ahead, which might be actually impossible. Also, what features you use is a design choice. Do you use as features for a data point here the short-term history over the last 5 days or over the last 100 days? What could be the reason to not use for predicting the next day temperature, for using only the previous 5 days temperature and not the previous 100 days temperatures? Should we use as many features as we can get? Well, it turns out that if you use too many features, I like to denote the number of features by small n, the resulting models that you use, they might become too large. I will talk about measures for the size of a model in a second. So if you use too many features, the models become too large, and the problem with large models is that they might overfit. So we will hear about overfitting in the next rounds also, but loosely speaking, overfitting means you learn a model that does perfect predictions on a training set, but does very poor predictions outside the training set. And if you use many features, you will typically obtain a powerful model, a large model that can perfectly fit the training set, but doesn't learn anything useful. Okay, so that's the problem with using too many irrelevant features. But to some extent, what deep learning methods are good at, often very good at, they find out automatically what are the most relevant features. So they are somewhat robust against overfitting, because even if you feed them many irrelevant features, these methods find it out or make it easy to spot those irrelevant features and ignore them. So in a sense, deep learning using these artificial neural networks as models reduced the burden of finding good features. So it does somewhat this feature selection automatically. Or in other terms, you can feed whatever raw data you have into your deep neural network to some extent. Okay. Yes, so then we distinguish different types of machine learning or deep learning problems by the type of the label. So if the label, the quantity of interest, is some number, like a temperature or a distance or a duration, then we call it a regression problem. And in these regression problems, we can make use of the numeric structure of the label space. So we can compare, for example, we want to predict the label being the temperature, and the true temperature is 10 degrees. And our deep neural network predicts 12 degrees. And then we have another deep neural network which predicts 15 degrees. So what we can do in the case of numeric labels, we can say this 12 degree prediction was better than the 15 degree prediction because it's closer to the true label. So we have some notion of distances between label values. And this we don't have in classification problems. So in classification problems, the label values have no numeric meaning. They are just discrete numbers or categories like cat or no cat or cat or dog. So we don't have a way to measure distances between label values. And this, in turn, means that we need different loss functions. So when you use deep learning methods for regression or classification, the most significant difference is the choice of loss function. So deep learning methods for regression differ from deep learning methods for classification mostly in the choice of the loss function that is used for training them. Yeah, and again, what you use as label, as the quantity of interest, is a design choice. And here I would like to point out one requirement by the European Union for trustworthy AI, which is human agency and oversight. And the design choice for the label, for what you want to predict, is a way to exercise human agency and oversight. So it might be unethical to use specific labels. For example, to profile or to predict if a certain human has a certain disease, which is a private information. So you might not be allowed to use this label. Does this person have this specific disease? So you're not allowed to use that label in some sense from ethical perspective. Okay. Yes, then there are different flavors within classification. So the most basic classification problem is to have two different label values. So either cat or dog, or either hot or cold. And here I would like to also show I use the same raw data as before. So this Finnish weather data, which we could use to define a regression problem, like predict the next day temperature, but you can turn it into a classification problem by defining a day to be hot if the temperature at 3 p.m. in the afternoon was higher than 10, or cold if not. So you can turn numeric data into binary labels. The same raw data can be used to define a regression problem, which is to predict the next day temperature, or a classification problem to predict if the next day is hot or cold. Then more advanced problems, or like more complicated classification problems, is multi-class classification, where we have more than two label values or more than two categories, like could be nice morning, nice noon, or nice day, depending on the temperature at 3 p.m. and 10 a.m. So we have three different categories or three different label values here. Yet another flavor of classification problems is called, or in general, machine learning problems is called multi-label problems. So we can have several quantities of interest for the same data point. So for the same data point, we want to know the temperature at 10 a.m. and the temperature at 3 p.m. So this, strictly speaking, this would be two different machine learning problems. One machine learning problem would be predict the temperature at 10 a.m. and another problem would be predict the temperature at 3 p.m. However, we could also define a label being a vector containing two numbers. So we can also have vector-valued labels. So this would then be an example of multi-label regression. An example of multi-label classification is, for example, to detect the presence of different types of objects in an image. So one label could be, does the image contain a car? Another label could be, does the image contain a person? And the third label could be, does the image show a tree or not? Okay. Any questions up to this point? So we are still talking about data. Data is a set of data points. Each data point is an object that carries information in the form of different properties. There are two types of properties. One type of property is called features. These are low-level properties that we can measure or compute easily. And another type of property are the labels that we want to predict. Or we need to ask somebody to help us providing the label, like a human expert. Okay, so it turns out to be useful measuring the size of a data set. And one way to measure the size of a data set is, for example, counting the number of rows. So let's say one data point would be one of these measurements. So we would have number of rows in this table would be the number of data points. But it's not always a good measure to count the size or like let's say the storage requirement of the raw data file. Because you could then say, I increased my data set just by copying this data as many times as I want. So I have one data point and I just clone it. I copy it, then I have many, many more data points. So it doesn't really bring more information. It's not clear per se if the amount of information in these data points is directly related to the number of rows in this data file. So that's why I like to have the term effective data size. And I here illustrate this by means of a time series. So assume a data point would be a certain state, a state of a pandemic, for example. Like the pandemic, like the number of COVID infections during some point of time. We would hear one data point, another data point, and the next data point. And often, this state doesn't change too much. So it might not change within milliseconds. So if I generate data points by sampling the state of such a system in a millisecond range, I get many, many, many data points, but they don't carry as much information as they take space on the hard disk. So this effective data size is the effective number of data points that bring additional information. And this is not always the same as counting the number of rows or counting the rows in a table. Just would like to point this out. And it's not easy. So I want to highlight here, it's not trivial to really measure the effective data size. But why is it useful to have a measure for the effective data size? Because we will later see, to do good machine learning or to avoid overfitting, we need to have sufficient training data in the sense that the effective data size of the training set has to be larger than the size of the model. So I will then also explain how to measure the size of a model in our second component. Okay, should we have a 5-minute break? Who wants a 5-minute break now? No, but I go with the majority. We continue with the second component, which is a model. And here I like this quote very much, presumably by George Box, which says, statisticians, like artists, have the bad habit of falling in love with their models. So one should be really pragmatic and not favor one specific model, except mine, of course. The one that I'm currently working on and publishing papers about. But I would like to really point out that sometimes it might not be the best choice to use deep neural networks. So I guess you can look up the Kaggle competitions, machine learning competitions, and then you might see that for some types of data, a random forests or linear regression might be the best choice. Nevertheless, it's good to know how to use deep learning methods. So if it's the right tool, you know how to use that tool. Okay, so what is deep learning about? Deep learning uses a specific representation of a map. So we want to read in the features of a data point, X on the left, we do some computations, some simple computations, and in the end we get an output, a prediction for the quantity of interest or label. So this is illustrated here as a graph. So here we have a bunch of data points. We know for each data point what is the feature value, and the label, so we can locate it on the plane. And we try out different hypotheses. So a hypothesis is just a map that reads in the feature and outputs a prediction for the label. So we try out different maps and try to find the best one. And these different maps in deep learning are represented by an artificial neural network. So this is only one map. How can we get different maps in deep learning? So does this structure represent only one single map? Well, in general, we have tunable weights. So each link here in this diagram carries a tunable weight that you can change. It's a factor, a number, that decides how much do you amplify the feature X in the first layer, and then in the next layer here, how much do you amplify the outputs of these neurons. So to each, to each link here, we have a tunable, a changeable, adjustable weight. And by tuning this weight, by changing this weight, we get different hypotheses. We obtain different maps. Okay, and yeah, what makes deep about deep learning? In deep learning, we use such signal flow charts for function representation. They are called artificial neural networks. We use a specific type of such networks. In particular, we organize these elementary computational units in the form of layers. So we have a layer is a group of neurons which is not connected within each other. So there are no cross connections within neurons in the same layer. But there are connections from the outputs of one layer, neurons in one layer, to the neurons in the next layer. So there's this sequence of layers that change the current states or the current outputs by applying simple computations in the form of combining the signals at the input of the neuron and applying some nonlinear function. So it turns out that this layer-wise structure is very useful and very efficient, allows to quickly search over large sets of different hypotheses, allows to quickly search over large models. Okay, so that's the basic structure that you will work in this whole course. That's the anatomy of a deep neural network. Okay, and there's a nice interpretation here that each layer implements a feature map. So what these deep neural networks do is they twist and turn around the features of a data point in a way that in the end you can apply a simple linear map to get good predictions. So you can think of each layer, adding a layer to a deep neural network tries to reshape the feature space or the representation of the data points as features in a way that in the new feature space, using the output of this added layer, the resulting data points are more aligned like a linear model. Yeah. So this is also related to kernel methods. In kernel methods, you also use this idea of using a feature transformation, and then you, in the new feature space, apply a linear map. But kernel methods use different types of feature maps. In deep learning, we use sequences of layers for this feature map. And what is also a big difference to kernel methods, we fully train, we also learn the feature map. So also the feature map is tunable. Okay, so now I have shown you the basic anatomy of a deep neural network. So the next question is, of course, why here 3 neurons in each layer And why 3 hidden layers? So which model should you use? Which deep neural network should you use? And to my understanding, we still don't have a theory that allows to answer that question in a very general sense. So if you tell me I have now this data, so today I had a visitor from the Helsinki hospital. She is interested in analyzing the organization of cells, cancer cells. And for example, to predict how they will behave when you use a certain treatment. And so this is a particular data set. And I would not know exactly what deep neural network structure you should use. So I'm not aware of a theory that allows to tell from basic statistical properties of a data set, you must use 10 hidden layers and 5 neurons in each hidden layer. I don't know such a theory yet. So here comes trial and error. Unfortunately, also in this course, you will see that much of deep learning is trial and error. So you have to try out different model structures and pick the one which has the smallest validation error, loosely speaking. But there are some guidelines that help you to make this trial and error faster. So you don't make too many unsuccessful trials, so to say. So first of all, the model should be large enough to contain a suitable hypothesis. The second requirement that I listed here is it should be small to fit the computational resources, because the larger the network, the more computation you need, and you only have limited computation available. Another requirement for having the model not too large or sufficiently small is to avoid overfitting, because a large model easily, if you use a very large neural network, you might be able to easily represent a very strange nonlinear map that perfectly fits your training data points. But do you like this map? So this map, this red line, might be obtained by training a big deep neural network in order to minimize the discrepancy between the predicted values and the actual labels of these blue data points. Let's say we got this red curve. This is the output of a trained deep neural network. Do you like this trained model? Do you think this red curve is a good predictor for the label Y based on the features? Yes? Yes. Very good point. Yeah. Yeah. May I ask, do you study mathematics? Do you study mathematics? Okay. Very good point. Yes. So per se, you cannot say if it's good or bad, because I only show you these 4 data points. It just fits these 4 data points. But if you know some domain knowledge, like as an engineer, so I also studied engineering a long time ago, we typically like things not to change too abruptly, because this is looks a bit unstable. So here we have like an infinite slope of this predictor. If we change the feature of a data point by a slightly bit, we get completely different predictions. This is somewhat unstable behavior, and we don't like that. So what we would like, at least for me in engineering, in my engineering way of life or perspective, some robustness or smoothness. And this was exactly pointed out here. We typically want the predictor to not change too quickly or to depend smoothly on the features. And yeah, by the way, how could we do this? How could we ensure this here? When we train a deep neural network on these 4 data points, we get this here, but we see it's not smooth enough. How could we enforce the smoothness? Well, we could add more data points by slightly perturbing these 4 data points by adding a bit of noise to the feature values. And this is called data augmentation. You will hear about in the roundabout of regularization. Okay. Yeah, so I've now said that when choosing the model, we must be be careful not to make it too small or too large, but of course, what is small, what is large? So how do we measure the size of a model? And yeah, just to point out again, by model, I don't refer to Johnny Depp or Claudia Schiffer here. A model is a set of hypothesis functions. So a model here is a set of different hypotheses, like this here. This is a model containing 3 hypotheses. So, for example, for this model, we could say the size of the model is 3, because it contains 3 different hypotheses. But what is the size then of the, for example, of the set of all polynomials of degree 2? There are infinitely many, so we cannot count it anymore. It's actually uncountable. So we need some different notions for the size of a model when we have infinite hypothesis spaces. And one such widely used measure is called the VC dimension. So the VC dimension is maybe the gold standard for measuring the size of a model. It's, I think VC stands for Vapnik-Chervenakovis. So I think they were Russian mathematicians, of course, who came up with this great concept of a dimension, VC dimension, as this measure for a model size. However, I like to make it more simple or more intuitive, and I define the effective model size as the number of data points that can be perfectly fit. So if the model size is 3, then any set of 3 data points can be perfectly fit. So let me illustrate this. When you have the model being the set of linear maps, the linear maps with any slope and offset or bias, then if you give me any 2 data points, I can always fit a straight line that goes through them. I can always perfectly fit the training set of size 2. Unless there's one tiny exception. When will it not be possible to find a straight line that perfectly fits 2 data points? Always these pathological cases. Yes? If they are vertical on top of each other, if they have the same features. Of course, because machine learning is about using the features to predict the label. And if you have data points with the same features, there's no way to predict 2 different label values. So unless the 2 data points are on top of each other, you can always find a straight line that goes through these 2 data points. And you can extend this, so when you have a degree 2 polynomials, so you say your model is the set of all degree 2 polynomials, or all polynomials of degree at most 2, then you will, let's say with probability 1, always find a curve that perfectly goes through a training set of size 3. So that's the basic idea how you measure the size of a model, by finding out how large can you make a training set while still be for sure able to perfectly fit it. Okay, but sometimes it's not so obvious that the model size, how the effective model size, what is the effective model size? Because you might even have a very large artificial neural network which can represent a lot of different hypotheses. However, you must also take into account the algorithm that you use to search over this hypothesis space. So it's good if you have a big model in theory, but you cannot search over it because you use some gradient descent method, which you will hear in round 2 or 3. And the gradient descent method operates in iterations, and in each iteration you can only explore a small neighborhood of your current model or current hypothesis or parameters of the hypothesis. So the number of iterations is essentially determining the effective model size for deep learning methods that use gradient methods. Okay, and yeah, as pointed out, so the model size should be not too small, so that it contains at least one nonlinear hypothesis that fits value data, but it should also be not too large that you do not overfit. So what I like to point out here is my Alex rule of thumb. which is an old engineering rule, have effective size of the training set 10 times more than the model size. Effective model size. So that's my rule. Then it's easy. Then you will most likely not overfit and learn a good model or learn a good hypothesis. Okay, so this rule of thumb connects the two design choices. Here comes into play the design choice for the model. This D is measures the size, the effective size of the model, and here is the size of the data. So here we relate the two design choices for data and model. Depending on what model you choose, you must get a sufficient number of data points. Yes? Very good. So how do you get this D? How you get the effective dimension? And I don't know in general. So for degree D polynomials, the effective size is essentially the degree. For linear regression, the effective size is the number of features. So this you can show with simple linear algebra, because you can see then that when you stack the feature vectors into a matrix, it has full column rank with probability 1 as soon as the number of data points is at least the number of features. So with simple linear algebra, you can find out the effective size of a linear model. I think this is called the fundamental theorem of algebra. You can show that the effective dimension or effective size of the polynomial model is the degree of the polynomial. But what the effective dimension of a deep neural network is, I don't know. This is highly non-trivial to measure. Does anyone know about recent research? How to measure the dimension or the VC dimension of a deep neural network? I don't know. So, but at least if we would know the effective dimension, then you could use my rule of thumb. But yeah, this is I think this is a topic or subject of research, current research, how to measure the effective dimension of a deep neural network. And one of the challenges is that it also depends on the optimization or search algorithm that you use to search over the model. This also impacts or limits the effective dimension. Okay, any other questions or comments? So we have now one relation between the design choices for model and data. Another one, more elementary relation, is when you look at the last layer of a deep model, you typically can already tell if you do regression or classification, and vice versa. So also if you do multi-label predictions, or you have a multi-label problem, then you have should have more than one unit in the final layer or output layer. Another example is when you solve or when you want to predict a numeric quantity, then it might not be useful to have in the final layer a nonlinear neuron, a nonlinear activation function, in particular a sigmoid activation function. So when you will hear more about this, I guess, in the next round. When you have a sigmoid activation function, you can only output values between 0 and 1. And if the quantity you want to predict is a temperature from -50 to +30 degrees, then you should not use in the output layer a sigmoid activation function. So in this sense, we also have restrictions or relations between the design choices. Yeah, because this was one main theme of the student feedback we received for the previous course edition. What are the basic criteria and guidelines to choose the models? So how do we know which model to choose? And in the end, it's a lot of trial and error, but there are few relations that constrain these choices. For example, as I said, when you do a regression problem, you should use a linear activation function in the final layer. Or if you do a classification problem, you might not want to use a linear activation function, but a sigmoid or a ReLU. Even ReLU might not be that useful. So a sigmoid activation function in the final layer. But I'm not aware of a theory, of a solid theory that allows to tell should I use 3 or 5 hidden layers. Okay, now the third component, the final component, which is the loss function. So now we have data points, objects that carry information, which are characterized by a feature and a label. And we want to learn a hypothesis out of a whole space or set of hypotheses. This set we call model. We want to learn or train a model to find a hypothesis that best fits the training data. And what does best mean? Well, for this we need a loss function. So we need some measure that tells us how well is a particular hypothesis doing in predicting the label of a data point from its features. So one way, maybe the most widely used loss function for regression problems is the squared error loss. So we take the predicted label, which is the output of the hypothesis. In deep learning, this is the output of a deep neural network, and we compare it with the true label, y. So we need to know the true label to evaluate the loss function here. And we square it. That's how we get a loss. Okay, that's one loss function, but again, also the loss function is a design choice. We could also use the absolute error loss. So we take the absolute value of the prediction error. And a design choice means we have to choose. So which one would you choose? Which one do you like more? Squared error loss or absolute error loss? Yes? The squared error loss, yes. Why do you like it more? Yeah, but also the absolute error loss has 0 only for the 0 prediction error. So these are both monotonically increasing. Why would we prefer the squared error loss over the absolute error loss? Well, we want to minimize. In the end, we want to find a hypothesis. So this is what we tune H to minimize this loss. And minimizing a function is typically easier when the function is smooth, because then we can use gradient descent. Then we can use local information. Then we just look around the neighborhood here a bit using the gradient. And we know quite a lot about how it's behaving outside this neighborhood. Whereas when you have non-smooth functions, you do not know from only looking at the neighborhood if you are here or up here. This makes minimizing such a non-smooth function more complicated, or in other terms, you need more iterations. You need more time to find the minimum for such a loss function. So it seems computationally the squared error loss is better. So why should we ever use then the absolute error loss? Computation is not everything. In machine learning, there are always two phases of a problem: computationally and statistically. So what are how computationally challenging is a machine learning problem? And on the other hand, what are the statistical properties of the solution to the problem? And it turns out when you have outliers in your data set, so you have a small number of data points where the label is erroneous, or like you have faulty measurements. So the label is any value, for example, very large. Then you amplify this in the squared error loss extremely, because the error or the loss increases faster and faster as the prediction error increases. So you have this very accelerated emphasis on outliers, whereas in the absolute error loss, you always have the same kind of the increase of the loss with increase of the prediction error is constant. So the slope is constant. And it turns out when you use the absolute error loss, the training becomes way more robust or immune against outliers. So when you have a few outliers in your training set, and you train a linear model with the absolute error loss, the effect of the outliers is almost negligible, whereas if you train a linear model with the squared error loss, just one single outlier can completely screw up the training. Okay, here's another example, the difference loss. How do you like the difference loss? This is a very nice function. It's linear. Should we use the, did you ever see somebody using the difference loss for training a machine learning model? Why not? Well, yeah, it goes, if we minimize the loss, then this would mean always we make as negative prediction error as possible. That would be the best. So typically a loss function, a good loss function, should be zero, should be minimum for zero prediction error. Okay, but it turns out that these loss functions for numeric labels, which is needed to define a prediction error. So without, if the labels are not numbers, then we cannot compute the subtraction here. So for binary labels, where we cannot subtract label values, we need a different loss function. And it turns out that one way to construct a loss function for classification is by using the same hypothesis as for regression, like a linear model. So we have h of x is a linear function, and we use two parts of this function. We use the sign of the function to classify, to find out the label or the category, and we use the absolute value of the function as a confidence measure in this classification. And this allows us to define a loss function that increases to the left. Here on the left means we make a wrong classification. So the label predicted by the neural network is different from the true label. And the more we are to the left, the more we are confident in this wrong prediction or classification. And these loss functions that I've shown here, this hinge loss and logistic loss, they punish increasingly wrong classifications in which we are more confident. And this is exactly what we want. On the other hand, for correct classifications, which is on the right side of the vertical axis, the loss function decreases. So we do not want to punish correct classifications, and in particular, we do not want to punish correct classifications in which we are very confident. And I have also plotted here the squared error loss, and you can see that for these classification problems, the squared error loss is not a good fit, because the squared error loss increases on both sides. So in particular, here the squared error loss would have an increasing loss for correct predictions in which we are very confident, which is the best case. So to the right, you predict the label is 1, where the true label is 1, and you are very confident in this prediction. This is the ideal case. So we want to have no loss at all here, whereas the squared error loss puts a very large punishment for such a scenario. Okay, so overall, the loss function again is a design choice, and we have at least 3 aspects that should be taken into account for this design choice. First one, statistical aspect. So is the loss function favoring a reasonable hypothesis? And this is often the case when you look at the squared error loss. So this would mean we want to have 0 loss for perfect predictions. This is exactly what we want. We want to have the predicted label to be equal to the true label. So here should be 0 loss and the minimum value of the loss function. This is what I mean by statistical aspects. Then we have to take into account computational aspects. So we need to be able to minimize the loss function quickly. This favors smooth and convex loss functions. But also the interpretation of a loss function should be taken into account. When you use this logistic loss, for example, this loss function here, and you get some value for your training set, like logistic loss is -3, I have no idea what this means, if this is good or bad. There would be another loss function, which is the the accuracy of a classifier, like counting the number of data points for which the true label equals the predicted label. And this loss function has a way nicer interpretation. Like, okay, this predictor for cat images has 99% accuracy. So this is a nice interpretation. But why would we still not like to use accuracy for training deep neural networks? So the accuracy would correspond to this stepwise 0-1 loss here. And it turns out that minimizing such stepwise functions is very difficult. Again, because just from looking at the neighborhood of a point here, you do not know if you are here or shortly before the transition. So you basically need to search over all possible hypotheses one by one to find the best one. So minimizing accuracy is computationally much, much harder than minimizing, for example, the logistic loss, which is, again, a smooth convex optimization problem. Okay, so to summarize, recap, we have these three main components of machine learning, which is first the data as a set of data points, each data point being characterized by features, which are the low-level properties that we can measure easily, and the label, which is the high-level property that we want to predict or want to find out ultimately. Second component is a model. A model is a set or a space of different hypotheses, and each hypothesis is just a map that reads in the features of a data point and outputs a predicted label, a prediction for the label. And the third component allows us to measure the accuracy or the quality of a prediction using a loss function. Okay? And all machine learning, every machine learning method uses a specific design choice for each of these components. So you can map out the whole landscape of machine learning using the model, the loss, and the data as the axis. And deep learning in this landscape is obtained for a specific slice on the model axis. So deep learning are any machine learning methods that use artificial neural networks, in particular deep artificial neural networks, as the model. However, you can still use the same loss as a linear regression, the squared error loss. You can use the logistic loss or cross entropy like is used in logistic regression. So these methods, basic machine learning and deep learning, differs mostly in the choice of loss, in the model, in the choice of the model. So instead of linear maps or decision trees, piecewise constant functions, we use artificial neural networks in deep learning. Okay, and in this landscape, you can also nicely illustrate the three main flavors of machine learning, which you might have heard about. One is supervised. So this is basically what I've talked about mainly today. In supervised learning, we have a loss function that is based on labeled data. So we need to know the true label of a data point to compute the squared error loss, for example. We need to know the label of a data point to compute the logistic loss. So these supervised methods, they differ in the choice of loss function from unsupervised methods. Unsupervised methods, for example, clustering. In clustering, we use a clustering error as loss function, or in PCA, or dimensionality reduction, we use a reconstruction error or a proportion of variance as a loss function. And in reinforcement learning, which is, I would say, the most challenging flavor of machine learning, we use a loss function that we can only evaluate point-wise. So you cannot, in reinforcement learning, you are not able to evaluate the function for all possible arguments. You can evaluate the function only at a certain point. During a certain time, you make a decision, like for a self-driving car, you take the direction. For example, you want to predict the steering angle, and the reward that you get is a crash sensor. So no crash means high reward, a crash means low reward. And this, in this picture, means you can only evaluate this function at single points. And this makes it very difficult because you cannot easily compute the gradient from evaluating a function at points. This is not possible for reinforcement learning methods. Okay. Yes, here's an overview, a nice picture that I found in the internet for the different models or the landscape of deep learning models. So as I said, deep learning uses as model artificial neural networks, and you can use many different structures for artificial neural networks. You will hear about one type which is called convolutional neural network in a later round. I think here we see convolutional neural networks and basic artificial neural networks in the next round. Okay. Yes, and just to point out, so the main part of this course will be about coding. So you will sit in front of your computer and implement deep learning methods in Python using particular this Python package Keras. And maybe you remember then from this lecture here, always these three components. You will see them in the beginning of your code. So you will see something that loads data, like this code snippet here. This uses ready-made data sets provided by Keras. Oh no, yeah, it reads in data from a given directory. So you can deposit images in a directory called pet images here and read in all these data points being these image files from the folder. Then you will have a code block that defines the model. This might look like this. And you see here this layer structure. So you build a neural network layer by layer. You start with the first layer entry block, and then you add layers. So this line here, for example, adds a batch normalization layer to the previous, what is previously in this X variable. Yeah, so it's this sequential structure of layers that you build. The only question is what sequence, in which order, and which layers you use. Okay, and then you will see at some point code like this, model.compile, where you choose the loss function. In this case, binary cross entropy, which is a more fancy name for logistic loss. Yes, so here, by the way, here you see two different loss functions actually. You see accuracy, which is used for something called metrics, and you see binary cross entropy. Does anyone know why we use two different loss functions? What could be the reason to use two different loss functions? Well, as I said, the design criteria for a loss function are you must be able to minimize it quickly, which is the case for this binary cross entropy function. You can use gradient descent. But you should also be able to interpret it like an accuracy, which is not delivered by this binary cross entropy. Therefore, we use the accuracy for the validation, where we only evaluate the function. So we'll talk about in a second about training and validation. So you might want to use different loss functions for finding the best hypothesis out of the hypothesis space, and then for after you have found or trained the model, evaluating this model on a validation set. You might want to use a different loss function there, which is more interpretable, like accuracy. Okay, so let's now have a quick walk through the cooking of bringing all these things together. And I mean, how do we bring it together? Using a .fit function. So nowadays, you don't need to solve training problems or optimization problems yourself. You use a .fit function that searches over all possible maps that are represented by a neural network with different parameter values. So again, with all this, with these links here, these edges in a neural network structure, is associated a weight that you can tune, or parameter. And the training of a deep neural network means tune or choose these parameter values to minimize the loss on a training set. And this is done by this .fit function. So with this .fit function, you find a hypothesis that best fits these blue data points, the training set. And then after you have trained the model, after you have found this good hypothesis, you evaluate it on a validation set. So you evaluate this hypothesis by computing the loss on the validation set, which is different than the training set. Okay. Yes, so, and you can do this with different models. So you can do this with different deep neural network structures, like using one layer, and here using 3 layers. So for each of these choices, you compute you train a model using .fit, and you get a validation error. And what you then do is simple. You pick the model structure with the smallest validation error. Okay. Yeah, and that's it. So that's the basic anatomy of your work as a deep learning engineer. And you repeat this until you found a model that has a sufficiently small validation error. Yeah. That's it. I mean, that's the trial and error approach. But you might use some tricks or some guidance to minimize the number of trials or errors. And one such guidance is by just looking at the size of the data and the model. So you can train a model with 1 billion parameters or 1 billion neurons on a data set with 10 data points. You can. And you will see overfitting. It might be useful to make this experience, but you should not do it permanently. So that's why you might want to consider this ratio of model size divided by data size. And if this ratio is very small, which it is often in deep learning, because deep learning uses so large models, this effective model size, think of it as being proportional to the number of neurons in your network. And when you have billions of neurons in your deep neural network, then you have effective size of billion, and you have maybe 100 images of your dog. So this is 1 billion over 100. And you are, okay, that you're here in the overfitting case. So you will see training error 0, you will perfectly fit your training set, but you didn't learn anything useful. So validation error is super high. Okay, so what you would like to do is you would like to change the effective dimension or the effective size of your model to be on a similar level as the number of data points or the effective number of data points in your data set. And you will hear in this course, in these different rounds, you will see many tricks or some of the most widely used tricks to bring this ratio down towards 1 or even below 1. So, I mean, how can you make this ratio small? Either you try to push down the numerator or you try to increase the denominator. Which one do you prefer? Well, let's start with making the denominator larger, so increasing the effective data size. And as I pointed out earlier, one very cheap way is to burn in your data set some robustness requirement. As an engineer, I always want things that are robust. So if you have slight changes in the features of your data point, the predictions should not change rapidly. Because my justification for this is, first of all, the features that you got, if they are from sensors or sensing devices, they are never perfect. Whenever you have a sensing device, a temperature sensor, look up the data sheet and you will typically find some statement, accuracy plus minus 1 degree or 0.5 degrees. You will never see a manufacturer of a temperature sensor that says this is 100% accurate. Never. You always have some intrinsic uncertainty. And you should not train a model that is more sensitive than this intrinsic uncertainty of your sensing devices that generate the features. So in general, you will always want to have some robustness to the perturbation of features. And one way to enforce this robustness is to increase your training set by augmenting each original data point by new augmented data points that are obtained by wiggling around a bit the features, adding a bit of noise to the features, but leaving the label unchanged. So in this case, I have increased the data size by 3. So I have just replaced each blue data point, or I have augmented each blue original data point by 2 perturbed data points. And I can do this with 5, 10 times, 100 times, 1,000,000 times. So this is one way to increase the effective number of data points or effective data size, and this brings down this ratio. And this is called data augmentation. Data augmentation will be practiced in round 4 or 3, I think. Yes. Okay, another example for data augmentation. When you want to predict if an image shows a cat, then you can be sure that a rotated cat image still shows a cat image, or a shifted cat image still shows a cat image. Okay, yeah, I just want to point out that this adding data points you can equivalently do in the loss function. So instead of adding these perturbed data points to your training set and training your big model on this perturbed data set, you can use only the original blue data points, but add this, the effect of these augmented data points as a loss function component. This loss function component is often called regularization term, and depending on the distribution of these augmented data points, you have different regularization terms. So if these augmented data points here, for example, are distributed like a Gaussian distribution, what you end up with here is the sum of squares of the weights in your network, or the ridge regularization term. So there's a one-to-one connection between the statistical distribution of these perturbations and the regularization term. So whatever you like more, if you are very familiar with handcrafting the loss function, use this approach. If you're not familiar in your favorite Python framework how to change the loss function, use this data augmentation approach. Yeah, I think this is something, because we have pointed out PyTorch. In PyTorch, I think you have more control over the loss function. So in PyTorch, I would go for this approach maybe. But in Keras, I'm not so sure how easy you can tweak the loss function. Okay, so instead of increasing the data size, we could decrease the effective model size. So how could we decrease this? Well, the most direct approach, make your model smaller. Kick out a few hidden layers. Okay. Another approach, freeze some layers. So don't tune the parameters or weights of some layers, but use a pre-trained choice for these, or use a pre-trained layer that you might have got from some other data set, which is related but not exactly the same as you want to train on. So you will hear about freezing layers in transfer learning. I think the round on transfer learning later. Yeah, and you can also find information about this on the Keras documentation, which is pretty nice. Okay, yet another approach to decrease the effective model size is to couple some of the weights. This is called weight sharing or parameter sharing. So you insist in having these two links here having exactly always the same weight, or these 5 links always have the same weight. That's how you reduce the effective model size. Does any one of you know which type of artificial neural network is this using a lot? This weight sharing, where you use the same weight for many, many connections in the network. What type of artificial neural network is basically living on this weight sharing principle to reduce the effective model size? Well, you can almost guess it from the names of the rounds we have. So we have a round on artificial neural networks, and then we have a round on convolutional networks. Yes, in convolutional networks, we use a lot of weight sharing, and one of the effects is that you reduce the effective model size and reduce the tendency of overfitting. Okay, yet another approach to reduce the effective model size, explore a smaller region of the model by using fewer iterations. Does anyone know how this approach is called? To reduce the model size by stopping early. Early stopping. So this is early stopping. Early stopping means you stop the iterations of a gradient algorithm to search the overall hypothesis space after a small number of iterations. And the effect is that you can only search that the effective model size is smaller, because you cannot search more than 5 steps apart. Okay. So, to wrap up, we have discussed about the main components of machine learning. Maybe the most important component is data, which consists of data points, being objects that carry information. These data points are characterized by low-level properties that I call features, and high-level properties that I call labels. And the overall goal of machine learning, in particular of deep learning, is to learn a hypothesis map that is able to predict the label of any data point just from its features. That's the game. That's the name of the game in deep learning and machine learning. What sets deep learning apart from general machine learning is that we use a specific type of model. In particular, we use as a model the set of all maps that are represented by a signal flow chart, and we call such flow charts artificial neural networks. So deep learning is about tuning the parameters of such a signal flow chart to best fit a training set. Okay. And yeah, so the outlook within this course now after you have heard about the main components of deep learning, I highly encourage you to look at these intro notebooks that Shamsi mentioned already. So try to log in to Jupyter Hub, try to register to our Slack, and yeah, we will have the Zoom support session on 27th, which is the Thursday at 2 p.m. and an in-person support session. So for those of you who have the opportunity and who actually prefer to be in live, to have a face-to-face contact with the core staff, you have the opportunity during Friday afternoon in the hall AS4 in the 2US building. Yes, so again, please join our Slack. That's the best way to get support and to get answers to your questions. Okay, thanks a lot. Are there any questions? Yes. Yeah. Shamsi. Oh, yeah, you need a two-factor authentication for this. No? Not for Jupyter Hub? Yeah. Yeah. Okay. Okay. Yes. Yeah. But also for my courses, you already need this two-factor authentication that you can log into my courses. But yeah, then you should also be able. Okay, any other questions? Okay, thanks a lot and have a nice evening.